Hello guys, welcome back to my YouTube channel. Today we'll be doing some integration drama with Feynman and Catalan. So let's get to it and you'll see the drama evolve. So what is the problem? What's the thing that's keeping us awake at night? Let's call that I. It's defined as the integral from 0 to infinity of x over hyperbolic cosine of x dx, otherwise known as cosh of x. Now, before we can do anything or even think about doing anything, I would like to remind you of the definition of the hyperbolic cosine of x. So the hyperbolic cosine of x, cosh of x, is defined as e raised to x plus e raised to negative x all over 2. Well, it's a good fact to be armed with. So let's implement that now. So I can be rewritten as the integral from 0 to infinity of x 2x, actually, because the 2 goes on top, and in the denominator we have e raised to x plus e raised to negative x dx. Now we can convert these negative exponents into a positive exponents by, say, taking the LCM. So we have 2x times e raised to x all over e raised to 2x plus 1 dx. Now just look at the form of this thing. So we have 2 times the integral of from 0 to infinity of x times e raised to x over e raised to 2x plus 1 dx. So now looking at the form of this thing, we have an x that's not an exponential term, and we have this exponential fraction over here. So why don't we use integration by parts? Because if we differentiate this, for example, and say we integrate this, for example, and looking at it, it's pretty easy to integrate. I mean, exponentials are probably the easiest to do calculus with. So differentiating x will give us 1, so we can get rid of this x, and we can quite reasonably simplify everything if we integrate this. So let's try that. Let's do integration by parts on the entire thing. See you on the next page. So we plan to do integration by parts on this thing. So let's just find the antiderivative of this thing separately first before proceeding with anything. So we don't need these limits of integration to find the antiderivative, essentially. So this actually calls for a u substitution. So say we have u equals e raised to x, so du is e raised to x dx. So we'll have du over u squared plus 1, right? Because e raised to x, the whole thing squared, is e raised to 2x. That, if you remember your formulas of integration, that's inverse tangent of u. And I'm ignoring the constant of integration by now because we don't need that in our integration by parts process. And what was u? It was the inverse tangent of e raised to x, right? So let's remember this. Let's keep this thing at the back of our heads as we preserve some space over here. So finally, yes, what's the antiderivative of this term? Because we needed to integrate that, right? And we integrate both the times. So keeping x as it is, the antiderivative, if you remember correctly, is the inverse tangent of e raised to x evaluated from infinity to 0 minus 2 times the integral from 0 to infinity. Now we differentiate this x term, we get 1 times the antiderivative of this term. So the inverse tangent of e raised to x dx. Now looking at the form of this thing, I actually want to use some u substitution. So say I say let u equal e raised to x. So du will be e raised to x dx. So dx will essentially be du over u. Now let's fix our limits of integration. So when x was 0, u will be e raised to 0, which is 1. And when say x was infinity, u will be e raised to infinity essentially, which is again infinity. Fine, so we have I as, we can actually make changes here also. So what was x? ln of u is x if we take natural log on both sides. So 2 times the natural log of u times the inverse tangent of u, and we again change these upper and lower bounds. So those will be from 1 to infinity, and minus integral from 1 to infinity, my bad, integral from 1 to infinity of the inverse tangent of u over u du. Since there was like no du, like no differential element in the first limit, we don't need to make the substitution for du over u in place of dx, because there was no dx in this part. So let's calculate this thing, plugging in the upper and lower bounds. So since it's infinity, we need to take the limit as u goes to infinity of taking 2 outside. Say we have ln of u times the inverse tangent of u minus 2 times, when you plug in 1, you have ln of 1 times the inverse tangent of 1 minus 2 times the integral from 1 to infinity of the inverse tangent of u over u du. Well, the natural log of 1 is 0, so this thing will go to 0. Now when you plug in infinity in the place of u over here, if you treat infinity as a number, you usually don't. If you do, you'll have the inverse tangent of infinity, and what's the inverse tangent of infinity? That's right, pi over 2. But the only problem is this natural log term, that if you say treating infinity as a number, you plug it in over here, natural log of infinity will blow up to infinity. So we just keep the limit as it is. This thing just went to 0, so we just have negative 2 times the integral from 1 to infinity of the inverse tangent of u over u du. So the 2's cancel out here, and finally we have pi times the limit as u goes to infinity of the natural log of u minus 2 times the integral from 1 to infinity of the inverse tangent of u over u du. And what was this? I, right? Well, before doing anything, we can't do much with this part, but we can certainly do much with this part. So let's just call the integral, forgetting the negative 2, j. So what's j? Let me just write it down. So j is, I'm not taking the coefficient into the definition of j. So j is just the integral from 1 to infinity of the inverse tangent of u over u du. And for the integration of this thing, you can't use any standard known elementary integration techniques. We need to use some Leibniz rule. You can call it the Leibniz rule, or you can say it's the Feynman integration technique. So let's do that on a fresh page, and hopefully you learn something if you don't know these rules already. So we had to actually find our j, right? And j was the integral from 1 to infinity of the inverse tangent of u over u du. And the way we proceed with our Feynman technique is you parameterize this thing. Say j of b is equal to the integral from 1 to infinity of the inverse tangent of, instead of just u, b times u over u du. So you parameterize it with a parameter b such that our original j is just j of 1. So when j, so the j when b equals 1, you can check 1 times u is u, is just our original question, right? It's just our this question when b equals 1. Well, so what do we do with parameterizing this thing? Well, you differentiate it with respect to b. So you say d of the j of b with respect to b is nothing but the derivative with respect to b of this integral expression of the inverse tangent of b times u over u du. And so we can take this derivative operator inside this integral, but it gets converted into a partial derivative because the integrand is a function of both u and b. So we need to be specific by using these partial derivative operators. So the tan inverse of b times u over u du. And now, well, now we are going to look at u as a constant because we are differentiating with respect to b, right? So we have the integral from 1 to infinity of 1 over u is taken aside. Now we have to use the chain rule here. So we have to basically differentiate the external function. So the derivative of the inverse tangent is basically 1 over 1 plus the argument squared. The argument is b times u, the whole thing squared, and the derivative of bu, right? The derivative of the inside part, right? According to the chain rule. So the derivative of b times u. So you can take u outside, and derivative of b with respect to b is 1. So you just have a u outside because it was treated as a constant when we were differentiating with respect to b. The best part is the u cancels out. That was actually the essence of parameterizing it this way and then differentiating it. So you can say on differentiating j of b with respect to b, we get a j prime of b function. So this is j prime of b. And now we can actually evaluate this integral. So we have the integral from 1 to infinity. The u's got cancelled out. So we have du over 1 plus b squared times u squared. Why don't we factorize the b squared outside? We have the integral from 1 to infinity of du over 1 over b squared, which can be written as 1 over b the whole thing squared plus u squared. And now we actually have a well-defined formula to calculate this result. So we have 1 over this coefficient that was within the square. So 1 over b is just b times the inverse tangent of the variable divided by the coefficient that was inside the square. So u divided by 1 over b is just b times u, but you evaluate it from 1 to infinity because it's a definite integral. So it's actually a weird fact because the derivative of j with respect to b is actually found out by calculating a weird integral. But that's how multivariable calculus works, I guess. So 1b cancels out. I have 1 over b times, when I plug in infinity for u, because these were limit upper and lower bounds for u. Instead of u, if I say plug in infinity, I'll have the tan inverse of infinity, which is pi over 2 minus, when u is 1, this is just the inverse tangent of b, right? B times 1 is b. So let me just separate this out into two terms. So I have pi over 2b minus the inverse tangent of b over b. Well, that's just our j prime of b. But we have the derivative of j of b, right? We need to get j of b back, but only for specific values, only specific values of j of b. So to get j of b back, we need to integrate j prime of b with respect to b. Okay, but this is going to be a definite integral, because we want j of 1, right? Because j of 1 is our original j. We want this. So one of our bounds, upper or lower, is going to be 1. So let's just assume that the upper bound is 1, and we also want to find a value of b such that this entire thing becomes 0. So notice that when b is 0, j of when b is 0 because I'm going to have the inverse tangent of 0, which is a 0 divided by u is a 0, and then this thing entirely will go to 0. So the lower limit is 0. Say if we had put 1 below and then 0 on top, we would have to switch the orders so that we don't have any unnecessary negative signs. And why did we do a definite integral? Because let me remind you, by the fundamental theorem of calculus, this will become, after evaluating the integral, j of 1 minus j of 0, and I just showed you that j of 0 is 0, and this is nothing but our original j. So this evaluates to our original j basically. So that's to say that our original j is the integral from 0 to 1 of j prime of b with respect to b. So, and we have an expression for j prime of b, right? So let's integrate that. So we have the integral from 0 to 1 of pi over 2b db. We can write this as two integrals because of the linearity, minus the integral from 0 to 1 of the tan inverse of b over b. Don't forget the db. So j is just going to be, but we can pull out pi over 2, which is a constant. Then integral of db over b is the natural log of b, but you have to evaluate that from b equals 1 to b equals 0, minus let's just convert our inverse tangent into its Taylor series, because there is literally not much that we can do over here. So the Taylor series for our inverse tangent is as follows. So we have, say, inverse tangent of x is going to be the sum from, say, n equals 0 to an infinity of negative 1 to the nth power. So negative 1 to the nth power times x to the 2n plus 1 over 2n plus 1. So it's basically, if you plug in every increasing value of n, you can notice that this is basically an alternating series of say odd powers. So we know the Taylor series for the inverse tangent of x. So why don't we just plug that in over here? So instead of this inverse tangent of b, we can write the sum from n equals 0 to infinity of negative 1 to the nth power times b raised to 2n plus 1, but again divided by this original b over here. So we just have 2n, but this is divided by 2n plus 1, and it's integrated with respect to b. Let's not forget that. So now notice that when we plug in b as 1, we'll have natural log of 1. So pi over 2 times the natural log of 1 minus pi over 2 times the limit as b approaches 0 of the natural log of b, minus, now assuming convergence, again assuming convergence, we can interchange the sum and the integration. So the sum from n equals 0 to infinity, now plugging outside all the terms that depend only on n. So we have negative 1 to the nth power over 2n plus 1, and when we say integrate this, we have b to the 2n plus 1, because power plus 1, divided by the new power. So we have again divided by 2n plus 1. So 2n plus 1 times 2n plus 1 is 2n plus 1 squared. But don't forget to evaluate that from 1 to 0, because it was a definite integral. Now notice that the natural log of 1 is 0. And notice here that when you say plug in 0, we have the natural log of 0, which is a negative infinite. So we have minus pi over 2 times the limit as b approaches 0 of the natural log of b, minus, now time to plug in the upper and lower bound. So when you plug in 1 over here, you're going to have 1 to the 2n plus 1th power. 1 to the any power is 1. So essentially we have sum from n equals 0 to infinity of minus 1 to the n divided by 2n plus 1, the whole thing squared, times 1, and then minus minus plus, but when you plug in 0 in the place of b, everything goes to 0. Well, great. Now say if we use some limit properties and say we suck up this negative. So we have the limit as b approaches 0. Basically use log properties, not limit properties, my bad. So if you suck up this negative inside the log can essentially flip its arguments. So instead of b, we can have 1 over b if we have a negative outside, and you suck in the negative. And then this series is as it is, n equals 0 to infinity of negative 1 to the n divided by 2n plus 1, the whole thing squared. Now why don't we perform a little change of variable here? So let's say u equals 1 over b. So as b approaches 0, u approaches infinity. So in the end we're going to be having limit as say u approaches infinity of pi over 2 times the natural log of u minus, then this infinite series is as it is from n equals 0 to infinity of negative 1 to the n divided by 2n plus 1, entire thing squared. Now this was basically our j, right? Whatever we had defined originally. So let's recombine everything. So now if you remember correctly, our original I was just pi times the limit as u went to infinity of the natural log of u minus 2 times whatever we found for j, right? So basically if you see, j is multiplied by a negative 2 and then just added back to this expression. So let's do that. Pi times the limit as u goes to infinity of the natural log of u, and we already know an expression for j, so just multiplying that by negative 2, we have, or let's just directly substitute j, and then later we can see how to multiply. So we have limit as u went to infinity of pi over 2 times the natural log of u minus the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 entire thing squared. So we have pi times the limit as u goes to infinity of the natural log of u, and then when you multiply, the 2 and the 2 cancel out. We have minus pi times the limit as u goes to infinity of the natural log of u plus 2 times the sum from n equals 0 to infinity of minus 1 to the n all over 2n plus 1 squared. And now the great drama is all about cancelling these terms, because positive and negative, right? I mean, isn't that a great fact? Because if say we didn't have this term, this term, just having this term, say letting u approach infinity and then natural log of that u would have made it blow to infinity, right? So that's actually relief, just like my last video. So all we are left with our in our I is just 2 times this crazy series from n equals 0 to infinity of negative 1 to the n divided by 2n plus 1 term squared. So let's see what we can do with this now. So we had our original integral I as 2 times the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 term squared. Now I want you to remember my previous video where we had square root of 2 minus 1 to the where we had the square root of 2 minus 1 to the 2n plus 1 power divided by 2n plus 1 squared. If you remember this video, if you remember this video, I think I can put a card up there, but if you remember this video. So for this question we had defined a general function x as, well, there was a sum obviously from n equals 0 to infinity even then. So if you remember, we had defined our a function f of x such that we had the sum from n equals 0 to infinity. Instead of this square root of 2 minus 1, we had an x to the 2n plus 1th power divided by 2n plus 1 term squared, if you remember this video. And then what had we calculated this thing to be? F of x to be, we had calculated that to be the definite integral of the inverse hyperbolic tangent of say t over t dt. But then we can even define that to be a definite integral from 0 to whatever x value this function had. So in our case there was square root of 2 minus 1, but in a more general case, say x. That was essentially what our f of x was. And in a video before doing this square root of 2 minus 1 series video, I had calculated this thing, or I think in the same video I calculated this thing to be half of the dilogarithm of x minus half of the dilogarithm of negative x. So we can actually convert this expression into one of these f of x types. So let's actually do that. So we have I, that is 2 times the series from sum from n equals 0 to infinity of minus 1 to the n over 2n plus 1 squared. So what's negative 1? So we have the sum from n equals 0 to infinity. What's negative 1? Negative 1 is nothing but I squared, right? So I squared to the nth power is I to the 2n over 2n plus 1 whole thing squared. Now if we want to convert everything in terms of f of x, we need 2n plus 1 power on top, and we just have a 2n, right? So why don't we multiply and divide by I? So if we multiply and divide by I, for example, our original capital I will just be 2 times the integral from n equals 0 to infinity of I raised to 2n plus 1 because of the I in the numerator, divided by 2n plus 1 squared, and the denominator can be just pulled outside because it's a constant, so 2 over I. Well, great, now we can actually convert this into one of our these dilogarithm forms, because we have directly established the relationship over here. And let me remind you that 1 over I is negative I, because if you take again multiply and divide by I squared is negative 1, so I over negative 1 is negative I. So we have negative 2i, and then by the formula we have half of the dilogarithm of x or whatever was within this 2n plus 1th power. So in this case it's I minus half of the dilogarithm of negative argument or negative I. We can cancel out these 2's over here, and by virtue of this negative we can flip the order of these terms. So we have we're going to be having I times the dilogarithm of negative I minus I times the dilog of I, and we can roughly estimate this value I to be 1.831931. Yes, it's a weird answer, but let me give you some more depth on this. So we got capital I to be I times the dilogarithm of negative I minus I times the dilogarithm of I. Okay, and what was this originally? Well, if you remember before, we introduced our f of x and did like a total memory recall, this was actually equal to 2 times the infinite sum. So the sum from n equals 0 to infinity of minus 1 to the n divided by 2n plus 1 entire term squared. Now let me tell you now that this is a very famous constant called Catalan's constant. Catalan's constant. So this is basically 2 times Catalan's constant. Now Catalan, there's not much known about Catalan's constant because we don't know whether it is irrational or not, let alone its transcendentality. So we don't know much about this, except we can just estimate this. As I said, we estimated this to be around 1.831931, and we also established an expression for this in terms of complex dilogarithms minus I times dilogarithm of I. So we actually established this relation without even knowing beforehand what Catalan's constant is. So for all the number files who could actually see Catalan's constant back in this step, that's give yourself a pat on the back. Otherwise we unknowingly derived an expression for Catalan's constant, which is, if we divide everything by 2, we have I over 2 times the dilogarithm of negative I minus the dilogarithm of I. So that's quite fascinating because it actually connects our estranged dilogarithm function to a very very distinct constant in mathematics. So I really hope you enjoyed this video. Please like, share and subscribe. Recommend my channel to your friends. You can reach me in the comment section. And stay safe. Peace out.